A321 field trip. Power plant, CFM 56-5B. The first part of this video field trip deals with the built-up engine unit equipment. The CFM 56-5B engine is designed in 4 major modules, which are the fan and LP compressor module, the HP compressor, combustion chamber, and HP turbine module, the LP turbine and turbine rear frame module, and the accessory gearbox module, where the different accessories are installed. For the moment, let's briefly see the location of these accessories. First, on the front face of the accessory gearbox, we can identify the lubrication unit, the engine-driven hydraulic pump, the ECU alternator. Notice the position of the hand-cranking drive pad used during borescope inspections. And the integrated drive generator, IDG. Now on the accessory gearbox rear face, we can identify the air starter, the fuel pump assembly, and the N2 speed sensor. Again, the fuel pump assembly with the hydromechanical fuel unit, HMU. The fan, which produces most of the thrust, consists of 36 fan blades made of titanium alloy. An abradable lining ensures fan blade tip clearance and improves efficiency. Here, between the fan blades, we can see the inlet guide vanes of the LP compressor. A fan blade can be easily changed in line maintenance after removing the spinner cone assembly. The rear spinner cone is fitted with trim balance screws. A reference mark identifies the position of fan blade number 1. In the engine inlet are located the pressure and temperature sensors related to the aerodynamic station 12, which are the PS12 pressure sensors, 3 located at the 1, 4, and 8 o'clock positions. And the T12 temperature sensor located on the upper part at the 11 o'clock position. Now we continue with the components located on the right-hand fan case. The ECU, electronic control unit, of the FADEC system is installed in this zone. It has 3 main sides. On the left-hand side, all the pressure lines from the different sensors enter directly into a pressure transmitter receptacle, part of the ECU. One of these entry ports is open because it corresponds to the P0 pressure sensor. On the bottom side, there are all the electrical harness connectors for channels A and B. Two of these connectors are for specific requirements. One is used for the engine identification plug and the second for the connection of test equipment. Note that the engine identification plug remains on the engine when the ECU is removed. This plug contains data characteristics, engine serial number, maximum thrust takeoff, etc. The same characteristics that can be read on the engine identification label plate. On the right-hand side of the ECU, as the ECU is air-cooled, the computer is fitted with a cooling air inlet and outlet interfaces. Concerning the electrical power supply of the FADEC, the ECU has its own dedicated alternator located on the accessory gearbox front face. Located above the ECU, we find the ignition boxes. The two ignition boxes are related to Ignition 1 and Ignition 2 circuits. Each box is designed to deliver high voltage to the ignition plugs through ignition leads. Precautions have to be taken before working on the ignition boxes. The voltage output can be dangerous. The ignition leads are then routed up to the ignition plugs. The part of the ignition leads along the engine core zone is fan air-cooled. The air is then discharged at the ignition plug coupling nut through a cooling shroud. There are two ignition plugs, one on the right-hand side of the engine at the 4 o'clock position corresponding to System A, and one on the left-hand side of the engine at the 8 o'clock position corresponding to System B. Now let's see the engine starting components. A pneumatic start valve is installed on the duct going to the pneumatic starter located on the accessory gearbox. The start valve, which is electrically controlled and pneumatically operated, has a manual override handle to manually operate the valve during abnormal starts. Before operating the manual override handle, the operator has to press a wrench button to release the butterfly valve actuator. The manual override handle can also be used as an external visual indicator to verify the position of the butterfly. Note, only operate the manual override handle with the starter system pressurized. Otherwise, you may damage the valve. When looking at the pneumatic starter, we can identify the servicing ports and the V-clamp installation. Now let's see the engine vibration components. All the engine vibration parameters are collected through a remote charge converter. This converter then sends the vibration signals to the aircraft engine vibration monitoring unit. There are two vibration sensors on the engine. One is installed in the LP compressor module on the number 1 bearing support. It is called the number 1 bearing vibration sensor, only its connector is visible from outside on the right-hand fan case. and the second, located on the turbine rear frame, is used as a backup accelerometer in case of failure of the number 1 bearing vibration sensor, which is not line replaceable. This second accelerometer is also used with the first one for balancing purposes. For engine speed indicating and monitoring, 2 speed sensors are provided on the engine. The one located on the right-hand fan case is for the number 1 speed, which is sensed at the number 2 bearing compartment. And the second, located on the accessory gearbox rear face, is for the N2 speed. Each of these speed sensors has 3 connectors. One for channel A, one for channel B, and the last for the EVMU. Now let's continue with the components located on the right-hand side of the engine core. But first of all, have a look at the fan discharge casing. When looking forward, we can see the struts and the fan outlet guide vanes. For borescope inspections of the LP compressor, 2 open holes are provided on the fan duct panels, located at approximately the 4 o'clock position. The HP compressor inlet temperature is monitored by the T25 sensor, located on the fan frame compressor case. On the HP compressor case, the engine is equipped with a variable stator vane system for compressor airflow control. The compressor stator vanes are in 4 unison rings. We will see the system in detail later on. Now, when looking at the HP compressor bottom line, we can see borescope ports. There is a borescope port for each stage of the HP compressor. At stages 1 and 2, stages 3 and 4, stages 5 and 6, and stages 7, 8, 9, for which the bolts are longer and bigger than the other ones. Now we continue with the combustion chamber section. The combustion chamber is equipped with 20 fuel nozzles and 2 ignition plugs. Fuel for combustion is fed by means of 2 fuel manifolds. Each of them supplies 10 nozzles. Each fuel nozzle has a shroud drain line connected to a separated drain manifold. Note that the fuel nozzles installed at a normal place are marked with a blue collar. The fuel nozzles mounted near the ignition plugs are marked with a silver collar, because they are of a wider spray type to improve lighting up. The fuel distribution for 10 or 20 nozzles is ensured by a burner staging valve installed approximately at the 6 o'clock position on the HP compressor case. This valve delivers fuel either to 10 nozzles at low power or to 20 nozzles at high power. Now have a look at the combustion chamber case where the borescope ports are located. 4 borescope ports are provided around the combustor case. 2 borescope ports are provided around the HP turbine case. These ports are used to inspect the HP turbine blades. Note that the igniter ports can be used for inspection of the HP turbine nozzle assembly. For borescope inspections of the LP turbine, 4 accesses are provided on the LP turbine case. For inspection of the first stage, use the same port as for the HP turbine. As for the 3 other stages, use the ports along the LP turbine case bottom line. On the right-hand side of the engine core, we can also identify other components which are part of the active clearance control system. We have the LP TACC valve and the HP TACC valve. The LP-TACC valve, which uses fan air taken in by a scoop in the C duct for external case cooling of the LP turbine. And the HP-TACC valve, which uses 4th and 9th stage air for internal cooling or heating of the HP turbine shroud structure. This valve is fitted with a visual open-closed position indicator. The rotor active clearance control valve will be dealt with later with the presentation of the other side. 2 T-case thermocouple sensors are installed on the engine, one on each side for the HP TACC valve control. When looking at the turbine rear frame, we can see the oil supply and scavenge lines for the aft sump. And a drain line to evacuate any water or fuel accumulated in the LP turbine case. Let's continue our tour around the engine. When walking up to the rear, we can see the center vent tube and inside the flame arrestor. Now we are on the left-hand side of the engine core. We can locate the rotor active clearance control and start bleed valve, RACSB. This valve uses 5th stage air to control the HP rotor cavity thermal expansion and 9th stage air to unload the HP compressor during the engine start acceleration. At the top of the engine, 2 attachment mounts are provided for attaching the engine to the wing. The forward mount and the aft mount. For the exhaust gas temperature, EGT, measuring plane. 9 thermocouples are installed around the LP turbine case, corresponding to aerodynamic station 49.5. The thermocouple's alumochromal material wirings are connected together to parallel junction boxes. And then to a main junction box. Here is the second T-case sensor used for HP TACC valve control. At Aerodynamic Station 3, HP compressor discharge, 2 sensors are provided for temperature and pressure sensing. One is the T3 sensor, located at the 11 o'clock position. And one is the PS3 sensor, located at the 9 o'clock position. On the pneumatic system, 2 customer bleeds are provided from the 5th stage for intermediate pressure and from the 9th stage for high pressure deliveries. A check valve is installed on the IP duct. An HP bleed valve is installed on the HP duct. And a bleed pressure regulating valve is installed downstream on the common duct. The bleed pressure regulating valve and the HP bleed valve are fitted with a closed-open visual indicator and manual override. For fire detection purposes, there are 2 fire sensing elements installed on the engine core. 2 more are located on the pylon zone and 2 others on the accessory gearbox. Here is the sensing element of the engine core left side. Each element is connected to its related fire detector responder housing. Note that in the hot section, the head is of the ceramic type. Remember, on the right-hand side, we saw part of the variable stator vane system. The actuation of VSV is performed by 2 actuator and bell crank assemblies. One is located on the engine core right-hand side, and the second is located on the engine core left-hand side. Each VSV actuator has a LVDT sensor connected to the ECU for position feedback. The left actuator LVDT is connected to channel B and the right to channel A. Notice that no rigging procedure is required on this system. The other system installed on the engine for compressor airflow control is the VBV, Variable Bleed Valve System. It consists of 12 VBVs. The system is actuated by means of a fuel gear motor which drives a master ball screw actuator and bleed valve assembly via a stop mechanism. The other 11 bleed valves are driven by means of a flexible shaft. The VBV positions are taken from the master bleed valve feedback rod linked to an arm lever fitted on a rotary variable differential transducer, RVDT, which sends the position feedback signals to ECU channels A and B. For the rigging procedure, make certain that, when the valves are fully closed, the mark on the RVDT is aligned with the mark on the arm lever. Note that the variable bleed valves are closed when the engine is shut down. They will be open during engine start. Before leaving the engine core section, have a look at the bundle junction box, where pipes, ducts, and electrical wirings are routed. Now, let's continue the presentation with the components located on the left-hand fan case zone. First of all, the fuel system components. When following the fuel feed manifold from the aircraft tanks, we arrive at the fuel pump assembly installed on the accessory gearbox. The fuel pump assembly consists of two pumps, LP and HP stages, and a fuel filter. The fuel filter, which is a disposable cartridge type, has a drain plug for drainage and sampling. For monitoring to detect if the fuel filter is clogged, a fuel filter differential pressure switch is installed at the 9:30 o'clock position of the fan case. On the accessory gearbox, the hydromechanical fuel unit, HMU, is fitted with the fuel pump assembly. The HMU has several torque motors and solenoids integrated on it, which are not line replaceable. If a torque motor or solenoid fails, all the HMU must be changed. The fuel is heated before entering the HP fuel pump and HMU. The fuel is also used to cool engine oil through the main oil-fuel heat exchanger and servo fuel heater. Part of the fuel is used as servo pressure by the HMU for the actuation of subsystems, that is to say, VBVs, VSVs, ACCs, etc. The fuel metered from the HMU then passes through a fuel flow meter. Then the fuel is directed to the combustion chamber. Part of the fuel is used for IDG oil cooling purposes. For IDG oil cooling purposes, the IDG oil cooler and the fuel return valve are located on the fan case upper part. The IDG oil cooler always ensures the IDG oil cooling by means of bypass fuel from the HMU. The fuel return valve ensures a fuel recirculation to the aircraft tanks for additional IDG oil cooling under certain aircraft fuel system conditions. And the ECU control depending on the engine oil temperature. An ECU, engine oil temperature sensor, is installed for that reason on the engine oil supply line going to the forward sump bearings.